So in this afternoon's session, we will have a couple of talks, and then the poster presenters will give us 1-minute summaries, like the brief on Tuesday, so just to prepare you for that. And we're going to start with Naaman, who's going to tell us about a big unsolved problem in the origin of life, and hopefully provide an answer, right? Chirality, he's going to talk about chirality.
Okay, thank you very much. And I realize that we are really heterogeneous audience here, and some people, for them, what I'm going to say is trivial, some for others it's completely unknown, so I will try to go between the drops and optimize. Okay, let's start with chirality. You know, chirality is a property of a molecule that tells us that this molecule comes in two configurations that are mirror image to each other, they are chemically identical, but like hence they have different symmetry. Now, the effect was the existence of chiral molecules was established in the late 19th century. It was a process, but at the end, Pasteur was the one that nailed it, and he found that molecules that come from biological origin, they are all have one handedness. And he also went further and stated that life do not exist without chirality. So chirality is part of life. It's interesting because till today, in this conference, chirality was almost not mentioned. And however, we all know that molecules, biomolecules, are appearing in one handedness. There are exceptions, but typically all our amino acids are what's called, they are L, namely the rotated linear polarized light to the left, while sugars, DNA, rotate circular polarized light to the right, and they call G. And this effect is called homochirality. Now, of course, it was an important issue because if you try to make drugs, you want to have the right chirality that will interact with biological system, and therefore chemists work hard to prepare chiral molecules with one symmetry or to separate from reaction. In the typical reaction, we get equal amount of enantiomer, namely the two handedness are appearing the same amount, and then we have to put effort in order to separate. But nobody really related special electronic or spintronic properties to the chirality, and nobody asked why nature, all through the evolution, kept chirality. Because if you think about it, keeping chirality means we reduce the entropy. This costs energy. Why it's so important for nature to keep chirality? For some reason, this issue was not raised, and the conventional wisdom that chirality is only structure. So now we will leave chirality on the side for a second, and we'll go to the electron spin, because electron spin is known from the beginning of the 20th century, and it's basically the angular momentum of the electron. The electron can have two spin states. We call it spin up, spin down, and typically they are degenerate, they have the same energy. And when electrons form bonds, then we know that in each orbital we have up to two electrons, and they must be of opposite spins. opposite spins means that the total spin of typical such bond is 0. And therefore, if we have molecules with all the molecules are paired, the spin is 0, and if you ask regular chemists, what about spin? Say spin is irrelevant. And spin, therefore, is related usually to cases where the system is unpaired electron, and that's cases of paramagnetic or ferromagnetic properties. Now, typically, the spin of the molecule, even unpaired electron, is not coupled to the molecular frame. This means that if I control the spin of the electron, I change it, it doesn't affect the molecule. Therefore, spins typically were not used to control chemistry. The exception is photosynthesis, where when you have singlet and triplet state, singlet means that we have the electrons with opposite spins, triplet means we have electrons parallel to each other, then we get different product in photoreaction. But beside this, in biomolecular reaction, the spin was not considered as an important parameter defining the outcome. Okay, what I want to show you, that due to the fact that we discovered, which we call the Chiral-induced spin selectivity, in short, cis effect, for Chiral molecules, spin is important even in closed shell systems. Not only this, there are special properties for electron transfer in Chiral molecules that affects everything that we understand in biology. So I put really strong claims. First of all, I claim that in biology, spin-controlled electron transfer is the common. It's not the rare, it's the common. Namely, the electron that is transferred in biology, and there are many cases where I will give you some examples, where electron is transferred, the spin defines the electron transfer. Namely, one spin is transferred better than the other. The second claim, that actually we cannot have oxygen-based life without chirality. And that's a very strong statement. So chirality, it's not coming with biology. As I see it, life could not exist as we know them, based on oxygen, without chirality. And I will try to go through it and explain to you at first what is the cis effect, the Chiral-induced spin selectivity effect. So I'm not going really in details. There are hundreds of papers published on it, but the idea is very simple. Think about electron, or if you like a child, going down this slide, okay? This is the Chiral potential. Basically, whole Chiral potential are helical. I will not elaborate on it. So what happens to a child going down such a slide? In order to keep him within the slide, there must be centripetal force acting on him. So the force will be from the left for one helix and from the right for the opposite helix. For the electron, this force in the rest frame of the electron is exactly like magnetic force, like a Lorentz force acting along the molecule. You know, the electrons moving in magnetic field, they tend to rotate, and this type of rotation is exactly like the centripetal force. So this it's effective magnetic field. There is no real magnetic field that you can measure, but it's an effective magnetic field felt in the rest frame of the electron. This can act on the spin just as a magnetic dipole moment, and therefore the two spin states of the electron split. So one gets stabilized, the other one gets destabilized. So now, going through the system, it's easier to go for one spin than the other. So which spin is go through depends on the handiness of the molecule and the velocity of the electron. Electron going downwards will have one spin stabilized, those going upwards will have the opposite spin stabilized. That's important. So what this effect does, it couples the spin degree of freedom, this angular momentum, with the linear momentum of the electron. If you want to think about it, it's like throwing American football. There are some American viewing audience, and as you know, when the football rotates, it's going farther away. The Israelis give always the examples of the bullet. When you shoot a bullet, when it's rotates, it's going farther away. And that's exactly what happens here. The spin can go longer distance because of this angular momentum effect. Another way to think about it, if you want to have an image, think about throwing a frisbee on the wall. If I throw the frisbee on this wall, it rotate this direction, it will go farther away. If you rotate the opposite direction, it will come back, and the opposite will be true if I throw the frisbee on the other direction. So it's very much like throwing frisbee on a wall. Okay, now I give you a simple example of experiment that we did, and the idea here, we measure the spin transport, spin selective transport through chiral molecules, and specifically here through DNA and oligopeptides. So we have a magnetic substrate, we put a monolayer of the chiral molecules, we come with a conductive tip of an AFM, and now we measure the current going from the substrate to the tip and back as a function of the direction of magnetization of the substrate. Depends on the magnetization of the substrate, once one spin will go in or the opposite spin will go in. Because the substrate is ferromagnet, and ferromagnet, all the spins are aligned the same direction. So here are typical results. This is the case of 20 base pair double-strand DNA. So here are how it looks for one magnet and therefore the other magnet. And you realize here in the semi-log scale that one spin has a lower threshold to get into the system than the other one. And the effect increases with the length of the molecule, and here are the results for double-strand DNA going here all the way to 12 nanometer, and you will see that we get spin polarization of about 60%. 60% is the spin when you take it from one direction minus the spin in the opposite direction over the sum. So 60% means that the ratio between the spins of the electron coming is 1 to 4. And here are the results for oligopeptide. These are alpha helix alanine, polyalanine. And you see we get also a length dependence, but I call your attention to the following. Look, the magnitude of the spin polarization here is about the same for DNA and polyalanine. However, here we speak about the length scale between 1.5 to 3 nanometer. Here we speak about 4 nanometer to 12 nanometer. So per nanometer, alpha helix is a very good spin filter. Much better than DNA. Now we can measure the spin as function of the length, the spin current as function of the length of the system, and you realize that for DNA here, these are 40 base pair DNA, one spin almost doesn't decay. The current almost doesn't decay with the length, while the other one decays very fast. As I mentioned, the one that doesn't decay is because we coupled the spin with the linear momentum. So for the electron to scatter back, it means that it has to flip the spin. Flipping spin is a highly improbable phenomenon. So that's an indication that nature may use this property to transfer electrons for long distance. Now I want to concentrate, because I don't have much time, I want to concentrate on specific reactions and to show you that why chirality is really essential for life, and I will concentrate on the reaction of oxygen. So let's start with the first process. It's artificial water splitting. In biology, it's basically equivalent to the photosynthesis. But let's concentrate on the artificial process because it's easier to understand. So what we do there, we take water and we produce hydrogen and oxygen by transferring 2 electrons from the water. So now we have 2 OH minus in the system. We have to transfer 2 electrons first to form 2 OH radical. And the OH radical forms, we want it to form O2 and hydrogen. And immediately you realize, if you remember what you learned in first year quantum mechanics, that there is a problem. What is the problem? We have OH minus. OH minus is a singlet. As I said, 2 electrons are with the opposite spin. Now I transfer 1 spin. Let's assume that now the OH is left with 1 electron pointing here, but the other OH minus, that should combine with this OH, give the opposite spin, because we have no control over which spin was transferred. And therefore now it may have the opposite spin. Now these 2 electrons, they are pointing opposite to each other. So when we combine them, they form singlet state. However, singlet state correlate with hydrogen peroxide. You cannot form, according to quantum mechanics, oxygen, because oxygen is a very special molecule. It's a molecule that is the ground state, it's a triplet state. Namely, it has 2 electrons pointing in the same direction. So you see immediately that there is a problem. However, if we have a way to force the system to transfer only 1 electron with 1 spin, then the 2 OH will have the spins parallel to each other. This is triplet, therefore we can form oxygen, and we cannot form hydrogen peroxide. Sure enough, what was found by many trying to do artificial water splitting, that first of all they need higher potential than thermodynamic dictates to form the hydrogen, and secondly, they have byproduct of hydrogen peroxide that destroys the system. So what we did, we took electrode and we coated it with chiral molecules. Now, because we have chiral molecules, the OH minus that has to give the electron to the electrode can transfer only 1 spin. And therefore, all the OH that will be produced will have the same spin. And therefore, we're supposed to get triplet. And sure enough, look here, there are nanoparticles on the surface. If they are coated with acyl, that's iron oxide here. If they are coated with acyl molecules, we get this amount of hydrogen production. If it's chiral, we get much higher hydrogen production. That's nice, but what about hydrogen peroxide? So here we can put an indicator that becomes yellow when we form hydrogen peroxide. And you realize that if we have achiral system, or system not coated at all, we produce a lot of hydrogen peroxide. However, if the electrode is coated with chiral molecules, the amount of hydrogen peroxide drops dramatically. So the system behaves as we want it to behave, and that was one example. It actually is very relevant to application. You know, producing hydrogen now, it's a big thing. But now we can go to something even more fundamental in biology. It's the respiration. It's also relevant to application because fuel cells are working basically similar to respiration. So what happens in the respiration? We start with a triplet oxygen. The products we get, all of them, are singlet. As I told you already before, this is forbidden. It means that somehow we have to make the spin to flip. Making the spin to flip means that we have to pay price for it. We can do it several ways. One is to put on the electrode heavy metal, very heavy metal, that has large spin orbit coupling, and this will flip the spin, or we go to higher potential. Okay. In nature, people thought immediately that the cofactor and the enzymes, they are responsible for the spin orbit coupling. But then they found enzymes that involve in the respiration that don't have any cofactor. So it remains sort of a mystery, and somehow, apparently, we all live well without knowing how we get our oxygen. but, as you will see, it is an important issue, as the question is, can chirality be the answer? And of course, I will not tell it to you if the answer was not positive. So, again, here, we have oxygen. Again, oxygen reduction happens by transforming two pairs of electrons to the oxygen. That's how it works. And here it's a simple example. That's what you see here. It's an electrochemical measurement of oxygen reduction. When the electrode is either not magnetized electrode or magnetized electrode. And you realize immediately the potential is shifted to this is lower value, lower negative value, so to more positive because it's a reduction. It's shifted for the magnetized electrode versus the non-magnetized. So that's already an indication because when the electrode is magnetized, I give only one spin, therefore it works better. So that was the first indication. But then we took gold, and you realize gold already is a heavy metal, so it has a spin orbit coupling. But now we coat it either with achiral or chiral small molecules, and you see immediately that the potential shift to the low potential with the chiral system. But then we did something even more interesting. We took alkyl chains that are not chiral, and as we made the alkyl chain longer and longer, the potential shift to higher and higher, to the left, okay, which is it means higher activation energy. While when we put chiral, in this case it's oligopeptides, chiral oligopeptides, when we made them longer and longer, the potential was shift to the other side. And you see it here and here. So basically, here we show that chirality helps in reducing the barrier for this reaction. But as you will see in a second, it's not only barrier, but here what we have, we took the typical, that's gold, nanoparticles, used in fuel cells. We made it chiral. We know how to make gold chiral. We got a huge shift in the potential. Here, the result with the best catalyst used in fuel cells, when we coat the catalyst with with chiral molecules, it becomes even more efficient. So the chirality does something even beyond the regular spin-orbit coupling. And actually, if we measure the activity, we can increase the activity of the catalyst by an order of magnitude. And only to understand what's going on here, think about the oxygen, it's a triplet. If we come with two electrons that have the same spin, then we split the triplet like it happens with magnetic field, and we reduce the reaction we increase basically, we reduce the energy, and therefore we make the reaction to go faster. And you see it here, the calculation that were done with it. And in addition, we have an entropy effect, because in the case of non-chiral, we have 4 states that are involved in the process, while with the chiral molecule, there is 1 state that is involved in the process. Here, 1 out of 4 is reactive, here 1 out of 1 is reactive. So we have a dramatic reduction in the delta G, and this means that the rate is enhanced by about factor 50. And I will end with an example, how can we get chirality? Because, you know, the big question is, how life became chiral? So the experiment was done by David, who is here in the audience. He definitely deserved it. He suggested this idea. The idea is to take this vinyl pyridine and to electropolymerize it with a magnetic electrode. And what is interesting, you start in the reaction, you start with a chiral system, and here you realize already you have a chiral carbon, asymmetric carbon. And what he did the experiment inside the CD spectrometer, and you realize when the magnet is down, the CD signal increases with time, namely 1 enantiomerase form. When the magnet is up, you get the opposite enantiomer form. The EE we get, sorry, it's here. The EE we get here is 55%, which is quite dramatic. The E is the enantiomer excess. It's quite significant. And how it works, basically the idea is that you get the first monomer on the surface, the second monomer comes, and it can attach to the first monomer in a pro-chiral configuration, either one or the second. And now for the spin polarized electrode to go and to reduce the system, it's better to go through one system, depends on the polarization of the spin. So that's basically the story, and that's what we get here. So my conclusion is, oxygen-based life could not exist without chirality, and the spin polarization can induce chirality if the reaction occurs on magnetic surfaces. And there is a work that was done at Harvard. Perhaps you will hear something about it in the next talk. And here are the people that did the work. David is here, he can tell you everything about it. And thank you very much.
Okay, questions for Ron. Let's take that.
Ron, beautiful talk, studies from Utah. So, why spin is important and chirality important in electrochemistry. But in actual biology, when you have a chiral molecule that has no electric field applied to it.
Oh, wait, stop. Okay, I have to correct you immediately.
Okay.
And that's something, it's really amazing. You have to appreciate that any contact between two molecules, any contact between any two molecules, means that there is a field applied on the molecule. In the simplest case, it's induced dipole. As we know, even two argon atoms touching each other, they polarize each other. But in case of molecules that are different, because they're different in electrochemical potential, you get real charge rearrangement.
Yes, but
And only to, I didn't say everything we did, but we did experiment on spin transport in proteins, and you see, we have an experiment, very simple. We put a dye inside the protein that interact with another protein, and we measure the interaction by exciting the dye with circular polarized light. And what we find, that one circular polarization is affecting the process, and the other one not.
But the dyes have dipole interactions. I mean, dyes are different. So if you have actually just a chiral molecule, I agree that if you have ions coming around, you are going to have a field that is going to fluctuate. But the probability of getting a spin up or a spin down electron in the chiral molecule in the solution would be almost equivalent, wouldn't it? Because the fields would just fluctuate, like the ions would come and go.
No, we don't. I don't. You have to understand. You ask on average, yeah, of course it will be zero. But now I'm speaking about the collision itself. In the collision itself, there is directionality and there is a field. And that's what makes it. Yeah, on average, I don't claim that if you do EPR in solution of neutral system, you are going to see signal.
Thank you.
Okay. Hey Ron, great talk as always. I was going to ask you a question about the water splitting reaction. So you showed that you use magnetite nanoparticles coated with chiral molecules. I assume that was to get the spin polarized electrons from cis-Fa. But what I'm wondering is if you don't coat the magnetite nanoparticles with chiral molecules, but just magnetize the surface.
Sorry, you're mistaken. It was iron oxide nanoparticles,
yes.
Not magnetized. They were not magnetized.
Yes, I said magnetite.
Magnetite. We use gold nanoparticles. We publish work on many systems.
Right.
So even you don't. It's true. If you use magnet, you can do the same thing by simply use magnetic electrode.
Okay,
it was done.
Okay, that's what I was asking.
No.
Like without using any chiral molecules?
No
just
chiral
using
molecules, you use magnetic electrode. The only problem with magnetic electrode that typically it's not stable under the condition. It's highly, pH is very high in this reaction typically.
Oh, I see. All right. Thank you.
Yeah. Again, a naive question, since I never heard organic chemistry or even electrochemistry. There's been a lot of talk in various biological systems of detecting magnetic fields on the basis of electronic reactions. It sounds like this offers a new way to think about the possibility there. Have you done that?
Okay, we didn't do it. There are people working on it, and only to elaborate on it, the idea, people think that you create either by photons and so on, by radicals. In biradicals, now the question is, okay, you have this biradical, and we know that biradical, the spin in biradical, the spin state is split by magnetic field, even a small one. But the question is, now, how do you detect it?
Right, that's why you're offering.
Yeah, and here we offer that the electron transfer from this biradical to the whatever sensor you have will depend on the relative rotation of the spin. Actually, it's a little bit more involved. It has to do with hyperfine interaction, but I'm not going to. But true, yeah, it's definitely true that you have a new way to sense spin in biology, and therefore you have a new way to sense direction of magnetic field.
Okay, thank you. Very nice talk. Very interesting. I have one more, sort of a different take on chirality. You know, if you think about Louis Pasteur's experiment, he demonstrated that assembly requires homochirality, right? If you have a racemic mix and you crystallize it, it will resolve into homochirality.
Not all molecules.
Yeah, but all complex molecules, right? So it's a general. So if you want to make complex assemblies, you simply must have homochirality. If you make a racemate of a polypeptide, you cannot make a peptide bond. You cannot make an alpha helix. You cannot do assembly with racemates. So, I mean, Louis Pasteur showed that with crystals, but that's definitely true for polymers. So it seems like if biology requires complex assemblies, it simply must be homochiral. There's no way around it.
Okay. It's true, basically it's true that it has to be homochiral, it cannot be, but why chiral at all? That's the question. I agree with you.
Because
once you have chirality, no way that you can get assembly.
Well, I mean, if it's chemistry, I mean, if it's carbon, it's going to be chiral. So,
No question. I will put the two questions here. And I didn't ask the question why homochirality. I asked why chirality. Homochirality, you're absolutely right. Once you are going this on one track, from my point of view, it doesn't matter if it would be the opposite chirality. Once you go one of them, you're stuck with it.
I see. Okay. All right. Good. Very nice.
All right, let's do one last question here.
Thank you for the presentation, and this is very challenging claims here. If we assume that you have a charge transfer which is chiral dependent, and also if we assume that it can change in specific system the chirality of macromolecule, it's possible to trace this in time, as time-dependent chirality, to measure charge.
Okay.
Do you have this?
Yeah, the answer is yes. In principle, for example, in all this production of a chiral system from achiral system, there is time. It's a time-dependent process. So
What is the time scale?
Okay, there are two time scales. The reaction rate, it can be very slow. The electron transfer process per se is very fast. So, but if you take an average signal and you ask, I want to monitor the formation of chiral product from achiral product, then it's a regular reaction rate, and it's very slow.
And this fast branch, how fast is this? Approximately in
They're very fast. It can be picosecond.
Great. I'll be happy if this I heard 15 years ago. But okay, thank you so much.
All right, we're actually going to have one last question.
Yes.
Anton.
Thank you. So I just want to clarify something. So you mentioned two-way effect. So the effect of redox reactions on the emergence of chirality and the other way around. And you are trying to make a claim that both of them are important. So I just want to make a couple of notes here. It appears that at least at the early times, at the times of origins of life, there was not much of oxygen on a planet. So all this oxygen business that you're talking about would probably be important later at about 2 billions at the emergence of eukaryotes. So it may be possible that the chirality would emerge due to some other important processes or requirements, but for the other part,
By the way, only a comment here. If you relate to sulfur, it's the same story.
Oh, to sulfur it's the same. Okay. So then, okay, maybe you can elaborate on that, please. So that's. And for the second part, for the importance of chirality, do you know, have you surveyed if those cytochrome oxidases, if someone tried to make a synthetic version of that would not be chiral, would it be performed in the same way? Have you tried to do any calculations on those? Thank you.
On what system, you mean?
Cytochrome oxidases.
No, I don't. That's tricky business. To make it achiral, I don't know how it can be done, but you can. You know, we did as close as it's possible. You take chiral versus achiral molecule, simple molecule, and transfer electron, and you check what happens to the oxygen. But to make enzyme that will be achiral, I don't think anybody imagined to do it.
Okay, well, let's thank Ron again for a very interesting talk. And our next speaker